going on? Okay, so when we look at this next section, like I said, we're going to be talking about how to graph these rational functions. Rational functions would be anything that involves a fraction. And the reason why we talked about those undefined values on our bell ringer is because it's going to come back in when we're dealing with these kinds of graphs, because you're going to have a fraction, which means there's going to be a denominator. And we have to think about the numbers that wouldn't be good for our graph here. And we're going to talk about what those are, how to find them, and what they look like when you're actually putting them on the coordinate plane. Okay, so we're also going to talk about domain again a little bit today. We've talked in the past about like domain and range and how to write that in both like interval notation and set builder notation. So we'll see a little bit of that again today. And then we'll talk about these things called asymptotes, and we'll talk about how to actually graph these. Okay. All right. So the first thing I want to just review with you guys is how to find the domain of a rational function. Domain would be those x values that work. And so this comes back into what we did in our bell ringer. We have to really focus on the x values that don't work and then being able to write our domain values from that information. So for example, when you have a rational function, it might look something like this. You've got maybe a polynomial in the top and a polynomial in the bottom. It could be really simple, like x plus 5 over x. It could be x squared plus 3x plus 5 on the top. And it could be x minus 2 on the bottom. Like they can kind of write those however they want. And so you even see an example right underneath it. It says x squared minus 25 all over x minus 5. That's a rational function. Okay, it's a fraction, and both parts of the fraction are made up of polynomials. They have x's and numbers and plus and minus signs. Okay, like we talked about on our bell ringer today, I would first kind of zone in on the bottom half, that x minus 5, because this is where my domain is going to be affected. So you can see what they did here is they're just setting it equal to 0, and they're solving for x, and you get 5. So the domain cannot include 5, because if it is 5, our bottom becomes a 0, and we can't have that on a fraction. So then you can see down below how they're writing that the two different ways. Remember, interval notation is when you're describing what the domain values could be. And so they're saying it could go from any number that's negative infinity all the way up to negative 5. So any of your x values that are from like a little bit above negative 5 to a negative infinity. So it could be negative 6, negative 7, negative 10, whatever, or the other side. So it could be anything bigger than that 5 and go on to infinity. But at 5 is where the issue lies, and we can't include 5 in this. We could get just a little bit above 5, like 5.0000000000001, and that would work. Or I could get 4.999999999 forever, and that would work too. But at 5 is an issue. They also have that written in set builder notation too. That's just another way to describe the domain. It's written just a little bit differently. You have kind of those more squiggly brackets. X is the value that we're kind of talking about the restriction on. And then it says after that, x can't equal 5. So let's take a look at this next one. Again, we're only really focused right now on the denominator. So if you guys look at the bottom piece here, how would you factor this? Good. X plus 1, x minus 1. It's the difference of two squares situation, so it factors like that. If you set those equal to 0, what do you get for x? Good. Negative 1 and positive 1. So x can't equal those two values. Okay, so let's write this in both set notation and interval notation. So let's just practice that. So if I look at my numbers here, I could have anything that's smaller than negative 1. So I could say negative infinity. And I could go all the way up to negative 1, but I can't include negative 1. So that's why we have parentheses around that point too. Because remember, the parentheses mean we're getting close to that number, but we can't actually equal it. If it was equal to, you'd have more of the hard kind of rectangular bracket. Okay, then I can have anything between negative 1 and positive 1. So we're going to use that union notation. Remember, those are those U's that kind of say like this is shared. So all of this is kind of going together. I could go between -1 and +1. Anything in between those numbers is okay. And then how would I write the last one? 1 to what? Infinity, because it can go on forever to the right. So you'll see in my notation wise, the 1 and the -1 are from the values that we found a little bit ago. That's interval notation. Now let's talk about set builder notation. So set builder is you use that kind of squiggly bracket. You're going to write x with the bar. And we're going to say x can't equal what two numbers? -1 and 1. So if you would like to, you could write plus or minus 1. Or you could separate them out. You could say x can't equal 1 and x can't equal -1. So you could just list them, like separating them by commas. All right, let's take a look at the bottom, the next one here. The denominator on this one says x squared plus 25. Okay, this one doesn't factor like that top one did. I can't write this x plus 5x plus 5. It doesn't work the same way. We don't have a rule for like the sum of two squares. We only had a rule for the difference of two squares. So if I actually just set this equal to 0, how would you guys start to solve this problem? Okay, so I'd have x squared equals -25. And then what would you guys do? Square root it, because I have to get rid of that square. What is the square root of a -25? 5i, right? Plus or minus 5i. Okay, when you're talking about graphing, are we graphing imaginary numbers? No, we're only graphing real numbers. So these are imaginary numbers that would cause issues. They're not going to show up on your traditional XY coordinate plane because they're not real. So because that's happening for this one, there really is no restriction on my X values. So I could write out for like, if they asked like, what are your domain values? I could say all real numbers work. Or if I wanted it in that interval notation, I would just say anything from -infinity to +infinity is going to work. Because the imaginary does not impact what my restrictions on my domain are going to be, since they're not technically real numbers. Now, most of the time going forward, we may not be writing out the domain specifically, but this is really what we're going to start most of our problems with, is looking at the denominator and figuring out what can x not equal. Because whatever that is going to impact how we start to graph it. Okay, so if you guys turn your page over, we're going to start getting into the graphs now. Okay, so again, at the top of the screen here, note imaginary numbers, imaginary solutions do not affect your domain. Okay, so that's why that solution was -infinity to +infinity. But the reason why we talk about these is because when we graph, we have these things called asymptotes. Some people might say asymptotes. It just depends on how someone wants to pronounce that. I've heard it pronounced both ways. But these are these values on your graph that start to cause issues. And we have vertical and we have horizontal asymptotes. Okay, so there's two different ones that we'll have to talk about. We're going to start with the vertical ones first, because this is coming right off of what we just discussed with our denominator. So when you're setting the denominator equal to 0, or you're thinking about the numbers that x can't be, this is going to play into these vertical asymptotes. So if I'm setting this equal to 0, that's what they're doing right here. That x squared minus 1, they're setting that equal to 0. They added the 1 over. So now it says x squared equals 1, and then they did the square root of both sides, and so they get plus or minus 1. Kind of like that example we saw on the previous page. So they're telling us down here that those vertical asymptotes would be at 1 and -1. So do you guys see on the graph where those are at? I have it graphed for you. Where are those points at? What do they look like on the graph? Straight up and straight down. How are they notating that on my graph here? What is it? The dotted lines are those x equals 1 and x equals -1. So when we're graphing these vertical asymptotes, we're going to be having these dashed lines that kind of go through them to kind of illustrate where those points are at. You're going to also think about these points as boundaries, okay? I'm going to put a little note here. Your function will never cross your vertical asymptotes. So like I was saying, they kind of act like boundary lines. Like they're saying you can't pass these areas that we have with our dotted lines. And if you kind of even look at the solid lines that are on my picture here, those are representing numbers that would fit into that equation up above that aren't 1 and -1. And you can see how they don't cross those lines x equals 1 and x equals -1. We have part of the graph that's like contained in between them. And then we have these two other branches, kind of one's on top here in like quadrant 1 and this other one's in quadrant 3. And those also are not passing those dotted lines. Okay, so if we have those vertical asymptotes, this is how we would graph them. I'm going to use dotted lines to show where they would be at. But in that other case that we saw on the previous page, there may not be always asymptotes. Like they may not have any like real effect on the problem because they're not real numbers. So like this one here, when we did this on the other side and we solved that, we got x to equal plus or minus 5i. Okay, that's what we just did on the bottom of that page before this one. And so those are imaginary numbers. They're not real. So on a case like this, there are not going to be any vertical asymptotes here because I could put in any number I wanted to for x and it's not going to cause a problem. If I put 0, 1, 2, 3, -1, -2, -3 in there, I'm still adding 25 to it and I'm squaring that number. It's going to always be positive at the end. So it doesn't really matter what number gets put in for x. So in this case, there would be like no restrictions on my graph at all. If you guys look at this next one here, what would you guys do to figure out if there's any vertical asymptotes that we need to be aware of? How do we find them? Okay, so if I set x plus 2 equal to 0, what does that become? So x cannot equal -2. That would be an issue. So on my graph, I'm just going to show you what that would look like again. I would come here to -2. I'm going to draw a dotted line up and down through -2 on the x-axis to represent that boundary. Okay, we're not going to graph this whole function quite yet because we're just not ready to maybe jump into that because there's some other things that we need to talk about still. But that gives you an idea of what those should look like. Again, last year when you guys were in Algebra 2, you did this. Like you were graphing equations that looked like this, and we talked about how to find the vertical asymptote and what that looks like on your graph. And then we did take it that step further and actually find points to use. We'll get there eventually. Okay, but the next thing we need to talk about on the next page here is horizontal asymptotes. All right, so these work a little bit different than the vertical ones did. So I'm going to add a couple of things for you just to be aware of and know about these before you start getting into problems. The first thing is that when you have a function, any function, they can have at most one horizontal asymptote. And I'm going to abbreviate that HA instead of having to write out horizontal asymptote. I'm going to do the same thing with the vertical ones. I'll write VA to kind of just shortcut that. So if you start to see me do that, that's what that means. So you'll never have more than one horizontal asymptote. You'll only have at most one, or you'll have none. You're not going to have 2, you're not going to have 3, you're not going to have 4. Now vertical asymptotes, you could have a lot, depending on what the bottom of the fractions look like. For horizontal, you can have at most 1, no more than 1 is allowed. Okay. Another thing to note is that your functions can cross these. That's also a little different than the vertical ones. Vertical kind of acted like boundaries in saying like we cannot pass these lines, we're stuck in between them or on the either side of them. Horizontal are a little different. Your function may intersect that line every once in a while, not always, but sometimes it does. And that's what they're showing you in this chart down below. They're giving you a couple of different situations. You can see the horizontal line is still using that dashed line there. So like this would be your horizontal asymptote, this one would be, and this one would be. And then they're showing you the different situations of where your graph might be. It could be underneath that line. It could be above that line. Whoops, it may even cross that line and kind of be on both sides of it. Last year when you guys were in Algebra 2, you talked about these as well, but you probably didn't really talk much about the logistics behind horizontal asymptotes. We just spent time on being able to identify it. We didn't really talk about the different situations that you might run into with this. So we are going to get into a little bit more of the meat today with these horizontal asymptotes and all the details that go behind it. So in order to find them, there's a couple of different ways that these can show up, and they kind of change depending on what you're maybe given in your equation. So the first case, I'm going to highlight this here, is when you're looking at your function, so you're looking at your numerator and your denominator, if the top and the bottom have equal degrees, that's going to be one situation for our horizontal asymptotes here. So remember, equal degrees just means that the top and the bottom would have an exponent that's the same amount. So you can see on this one here how they both say x squared, x squared. Do you guys all see that? The top has an x squared and the bottom has an x squared. Those are equal degrees because they're both squared. Okay, I'm just going to write that next to it. This has a degree of 2, and this has a degree of 2. When they have like degrees, you need to just focus on these two terms. And that's what they wrote down here. And you're going to simplify it. So you can see they wrote 9x squared over 3x squared. What happens with the x squareds? They cancel out. And then what's 9 divided by 3? 3. So that's how they got this number here. This is a y value, so we're saying that this would be the line y equals 3, which is right here on that graph. So they are showing you the graph over here because, again, we're not graphing quite yet. We'll get there. But this is what that would look like. And then when you just look at the function, you can kind of see it's getting really close to that horizontal asymptote for this one. It is not crossing on this one, but we will see some cases where it does start to cross. It just really depends on what the rest of the function looks like what else is happening after those leading terms. All right, the second case, still on this page here, is when the degree of the numerator is less than the degree of the denominator. I don't know why it does that sometimes. It's like I highlight it and then it just poof, disappears. Okay, so this time the top portion is going to have a degree that would be smaller than the bottom. So if you guys look at this fraction down here, what's your degree on top? Degree comes from the exponent. 1, because this is x to the first power. What's your degree on the bottom? 2. Okay. Again, you're only going to isolate those first two terms, like the ones that we were comparing. So they're putting 9x over 3x squared. They have that down here. This time, though, the x squareds are not going to cancel like it did on the last one. So we can see what they did is they simplified it by taking an x out of both, but there's still going to be an x on the bottom. And then that 9 divided by 3 is just 3. So we're left with this new fraction that says 3 over x. Okay. If you have a situation like this where you've got a numerical term on the top or like some term on the top and there's just an x on the bottom, that means that your horizontal asymptote is going to be at y equals 0. That's just like a rule to be aware of, is that anytime that it kind of breaks down like that, it's going to be y equals 0. And again, we can see that on my picture of my graph. All right, we've got one more case. If you guys turn your page over, we've talked about so far that the equal degrees, so the top and the bottom both say x squared, x squared. We just talked about the case where the top is less than the bottom. So the other situation would be when the numerator is bigger than the denominator, talking still about their degree. So if the numerator's degree is larger than the bottom, this is going to change a little bit. So if you guys look at this one, what is the degree of the top? 3, someone I think said. How about the bottom? 2. Okay. If this happens, there's not a horizontal asymptote. So that means there's no y equals line. There's something called a slant asymptote when this case shows up. We will talk about that and how to find it, but we're going to save that for a little bit later. But we will talk about the slant asymptotes, how you find them, how you graph them. All right, so down below, there's 3 problems here, exploring those 3 different options that we just talked about. Again, you're just going to kind of compare those leading terms. So if you look at this first one, what are you guys noticing about the degrees? They're the same because this has a degree of 1. So I'm just going to write D for degree, and I'm going to say 1. And this one also has 1. So if you guys do 4x over 6x, what happens? X's cancel out. Can 4 and 6, they can't divide, but can you reduce them to 2/3? So this would have a horizontal line at 2/3. So in that case, it's not a whole number, but we could estimate where we think 2/3 is at if we needed to graph that. Okay, what about the second case? What's the degree on the top? Good, 1. Oh, my pen. The degree on the bottom? 2. So if we set that up, 2x over 5x squared, what happens here? Take out one of the x's, so this one's gone, and the 2 goes away. So what are we left with? 2 over 5x. Okay, what did I say that means for your horizontal asymptote? What did the rule say? 0. Okay, the last case, what's your degree on top? And on the bottom? 1. So it'd be 9x squared over 3x. What does that reduce to? 3x. What does that mean? Not 0. This would have a slant one. So I'm just going to say no horizontal asymptote. And I'm going to say has a slant, which we'll get into later. Questions on distinguishing the difference between the 3? Okay. Let's see what we got left here. Okay, we're gonna try to do a couple of these with the graphs. So if you guys go to your next page, this is kind of going over how you can use transformations in order to help you graph rational functions. Again, with the parent graphs, that's like the original, and then you start to like add things to it, and it starts to move that graph around a little bit. That's kind of what's going on here. So the parent graph for 1 over x always looks like this first case. You kind of have, we call these like branches, these little parts of the function that are like those curved things. In the past, you've probably heard them called branches, like last year in Algebra 2. Because they're talking about like 2 halves of the graph, or there could be like 3 or 4. It just depends on what it looks like. That's the parent when it's just like 1 over x, and then here's the parent when it looks 1 over x squared. So you kind of get an idea of what the general shape is of those parent graphs, just like we know what an absolute value graph should look like. We know what a parabola should look like, and we've talked about in the past how you would graph the new ones based off of their transformations. Something else to know is on some of these you'll have even or odd symmetry. Remember, odd symmetry is when you negate the x value. So like if I had a function and whatever my x was, if I put a negative in, so if it was like a 3 and I changed it to a -3, or I changed the value of the x that was being put in there, it's going to impact what the rest of the function looks like. And so remember, odd means that it becomes negative f of x. So like when you negate the x, the whole entire thing becomes negative. And then even means that even if I put in a negative, it doesn't impact it at all, and it's going to stay the same. That also just lets us know that there's going to maybe be some symmetry about the origin, symmetry about the y-axis. Those are other things that we could maybe use if we're trying to graph and we don't have a bunch of points, or we maybe aren't looking for a bunch of points yet. Okay, so we're going to do a couple examples with the graphing. We'll see how many we get done here. I'm hoping to at least get this next page done, and then we might just stop there and try to finish the rest tomorrow. Okay, so we are going to also deal with all of our asymptotes, like finding the vertical and finding the horizontal. We're going to do all of that and then actually be able to graph this function. So let's start with the horizontal asymptote. That's when you focus on the denominator. What's the denominator say? X plus 3. If you guys set that equal to 0, what do you get? -3, okay? So I'm going to go over here right away, and I'm going to go to -3 on the x-axis, and I'm going to draw a dotted line going up and down.
That would be the vertical.
You're right.
Stuff.
Sorry, I wrote that in the wrong spot. I know. Thank goodness he's back there. Also, though, why would I have typed it backwards in my notes? I don't know why I did that to myself. Okay, now the horizontal asymptote, this is going to be a little bit different because we have like the leading, like the top has a degree of 0 and the bottom has a degree of 1. So we are dealing with that case. But do you see how they added on this -2 at the end? When they add on a number like that, it impacts what that horizontal asymptote is going to look like. Okay, so this is going to affect that because originally, if it was less on the top and bigger on the bottom, we talked about that would just be 0. But since that -2 is there now, it's actually going to push the whole thing down too. So if there's a number ever attached to the end, we'll have to reflect that and say this is going to be at y equals -2. So then I'm going to come over here, I'm going to go to -2 on my y, and I'm going to write that on my graph with the dashed line. So remember, the vertical, the one that goes up and down, our graph should not cross that line. It may cross the horizontal, potentially. So now what we're going to do is try to find a couple points that we could use to graph. If you have your calculator, you could type in this equation to help you find some points to graph. You can also use your parent graphs that we just talked about. Because my parent graph, especially this one, would look like that first one that was just y equals 1 over x. And so using your transformations, the +3 is going to make it move left, and this -2 is going to make it move down. So we could use that as well in order to help us graph. But I know when we start to get into a lot of the other graphs that start to get more complicated, we will start leaning on our tables to give us some values. So there should be a point at, like, is there any easy numbers in your table that we can graph? -4, -3. So I'm going to graph that point first. How about another one with like maybe just whole numbers?
-2, -4.
Okay.
I would keep the rest of the fractions.
Yeah. The rest are going to start to look really gross because you're dealing with these rational equations. Okay, they're not all going to be nice whole numbers. Okay, that doesn't work with these. So I have those 2 points. If I know that this, I'm just going to scroll back up for a second. I know that this is mimicking this situation because it's 1 over x squared. So I know what my branches should look like. I know then based on these 2 points that it should be kind of going like up in between this area from that point, and it should go down like this. Again, that's just using my knowledge from that parent graph I talked about, is that they should look like each other. Now, if you really wanted to graph some of those other points that showed up on your table, you could. You're going to have to do some estimating on where you think they are, because like we said, they're not nice numbers, but you could guess where you think they are on the graph. If you did that, though, you'd end up with the same picture I did. So I just used my parent graph in order to help me with that. Okay, so let's do one more. This one is going to look like that second case that we talked about because it's got a squared here. So again, if you kind of go back to that other page, that might help you a little bit. But let's kind of go through this. Let's focus on our vertical asymptote first. So that would be that denominator. So you're going to set this x minus 3 squared equal to 0. And what are you going to do to solve that? I'd square root it first. Yep. So this becomes just x minus 3. What's the square root of 0? 0. And then what would you do? Add the 3. So x can't equal 3. That's no good. So I'm going to come over here. I got to draw an up and down line through 3. Okay, now let's do our horizontal asymptote. This is similar to that other case where it is going to be like 1 over the x squared there. But because they had that plus 2, that impacts our horizontal. So instead of it just being 0, it's going to have to be y equals 2. So we saw that happen on the last one. It was just a negative 2 on that last one. So that's our kind of parameters here. And then again, you can use your table to maybe help you find some points to graph. 2, 3, and what?
4.
Those are the 2 points that you found that are nice, okay? And then again, I'm using from the previous page. If you just flip it back over, oh, I'm out of time. They should look like this. I'm just going to finish it real quick. Copy this down. That's what we're going to call it for today.